In this slide, I'm going after species that have 6 electron charge centers. Their electron geometry is octahedral. Their shape might be octahedral. It could change if you have lone pair of electrons. The first compound I go after is sulfur hexafluoride. Now remember, those elements bigger and including phosphorus can have expanded octet, so they can have more than 4 attachments. Sulfur in this case has 6 valence electrons. It also is borrowing or sharing 6 electrons with fluorines. 6 plus 6, you have 12 electrons. If you divide it by 2, you will have 6 electron charge centers or negative charge centers. Then we put sulfur in middle, and I'm going to have 1 bonding pair with fluorine. From the 6, I have 5 more left. Another one down here. Then I'm going to have a wedge with dashes in it to say there is a fluorine coming to you outside the plane of this board. Another one on this side. I will put a solid wedge here and say this fluorine is going inside the plane of your paper or my board. I'm almost done with Lewis dot structure. I'm going to put octet electrons for fluorines on the edges. They have no choice. They cannot have expanded. They need to look like the closest noble gas to them, neon. So only the central element can break the rule to be less than or more than. Now, I'm also going to do hybridization for this compound, although it's not required by IB, but for sake of later on, I have 1, 2, 3, 4, 5, 6 ECCs. Therefore, I'm going to mix my orbitals. S has only 1 orbital. P has 3 orbitals. Now don't forget D has 5, and let's see how many of the 5 I'm going to use. So I need 1, 2, 3, 4, 5, 6 attachments. 1, 2, 3, 4, 5, 6. So I'm going to mix this, and this is my hybridized orbitals. It's sp3d2. So this is hybridization of sulfur, or each of these bonds that you see covalent, sigma covalent bonds, they are sp3d2. Then again, not really important, but you're ready to go to college, so let's just have it. The bond angles, there is a square between these 4 wedge-shaped fluorines. Those are 90 degrees. And also the plane of fluorine going down and fluorine going up, so 90 degrees across the board. Now, what happens if you don't have 6 bonded pairs, rather one of them becomes a lone pair? A case such as bromine pentafluoride. Then I do the bookkeeping again only for the central element bromine, which can break the octet. Bromine is group 7, 7 valence electrons. I'm sharing 5 more electrons with fluorines, so 7 plus 5. Then again, I have 12 pairs. I divide by 2, I will have 6 negative charge centers or electron charge centers. So one of this bond becomes lone pair. I'll put it on top to respect the symmetry of the molecule. Then I will have the same remainder of the structure going, fluorine coming to you, fluorine going away from you on the same plane. I repeat it on the other side. If you also do it on paper, this becomes second nature to you. Let's put valence electrons for fluorines. Now you are a square on top, and in the bottom you look like a pyramid if you put planes of paper, so a square pyramidal is the shape. Your electron geometry was still octahedral. The bond angles are 90 degrees. These are all sigma bonds, they are all single bonds, and you still sp3d2 hybridized. Mixture of atomic orbitals to be able to produce molecular or bonding orbitals. Now the last possible shape for this category is, what if one more lone pair I have instead of attachment? And I go after xenon, a noble gas, tetrafluoride. Now xenon is group 8 noble gases. They have 8 valence electrons except helium. So 8 plus 4 additional being shared by fluorines. Then again I have 12 electrons. Divide by 2, you still have 6 ECC. So your electronic geometry is octahedral, but 2 of those ECCs are simply lone pairs above and below. Then do the rest as before, and you have 4 fluorines. Saturate them with their octet electron. Now realize you have a square in this plane, so they are 90 degrees away from each other. And then sp3d2 still is our hybridization. Even the lone pairs are part of the hybridized orbital.